Section 9.2, Sum and Difference Formulas. We already know a few trig identities, the Pythagorean identities, sine squared plus cosine squared equals 1, and then the other Pythagorean identities with tangent and cotangent and cosecant and secant and so on. Reciprocal identities, quotient identities, some of the more basic ones we've already covered. We're moving into the next stage of exploring some other identities. The first ones we're going to look at are sum and difference formulas. So let's have a look at these. The purpose of sum and difference formulas is to deal with situations like this, where we might have two things being added or subtracted inside of a trig function. Okay, and this is helpful because, first of all, if we have addition or subtraction inside of a trig function, we're kind of stuck with that. Like we can't just break this up into, cosine of x1 plus cosine of x2. It doesn't quite work like that. But once we're able to do this, it allows us to evaluate trig functions at some kind of unusual angles. Like that's what we're going to be doing in examples 1 and 2. And also this will provide, just more tools to work with when we're verifying different trig identities. Okay, so let's have a look at these. Let's start with cosine. So if we're taking the cosine of x1 plus x2, where x1 and x2, they could be variables, they could be real numbers. This is the same as cosine of x1 times cosine of x2 minus sine of x1 times sine of x2. Okay, so I'm sorry, I know that we all wish that this was just cosine of x1 plus cosine of x2, but it's not. Don't write that down. Don't write that down. Okay, this is the formula that we have to use to break up that sum. Okay, if there's a difference, cosine x1 minus x2, we have pretty much the same formula, except instead of a minus sign, we have a plus sign right here. Okay, so note that, it's kind of the opposite of what you think. If there's a plus sign in there, it's subtraction. If it's cosine of a difference, there's a plus sign in the expansion. Okay, and for sine of x1 plus x2 is sine of x1 times cosine x2 plus cosine x1 times sine x2. Okay, so here we have sine, cosine plus cosine sine, and notice that we're alternating those inputs, x1 and x2. And the difference formula for sine looks pretty much the same, but we changed this is subtraction in this one. Okay, so for the sine formulas, we alternate sine and cosine, cosine and sine. And if it's a difference right here, it's a difference right here. Okay, but if it's addition right here, it's going to be addition right here. All right, those are the formulas. Let's see how we might use them. Example 1. So I said that we will be able to use these formulas to evaluate trig functions at some kind of unusual angles. And I call this 5 pi over 12 an unusual angle because it isn't like, one of the angles we have memorized from the first quadrant of the unit circle, right? Because in the first quadrant of the unit circle, I'll just draw this out over here real quick. There are certain angles that we're really used to that we see all the time. Sorry, I can draw a better quarter circle than that, I think. Maybe not. We've got 0 radians. That's one that we deal with. Sometimes we've got pi over 6. Somewhere around there, we've got pi over 4. And we've got pi over 3. And then up here, we've got pi over 2. Okay, so yeah, if I see any of these, or, they could be multiplied by some integer, like 3 pi over 4, I also know how to deal with. Pretty much denominators of 3, 4, 6, or 2, or 1, I can deal with. But when I get something like this, 5 pi over 12, suddenly I'm at a loss, right? I don't know how to use the unit circle to do this. So rather than memorizing a whole bunch more angles so that we can deal with this, what we're going to do is get clever with these sum and difference formulas to see if we can rewrite cosine of 5 pi over 12 in terms of some angles we're more familiar with. So here's how we might do this. How could we take 5 pi over 12 and break it into a sum or difference that might yield some friendlier radian values? It turns out there are many different ways that we could do this actually, but how about we try and break this into a sum? I'm just going to try something like, okay, 5 I could break up to 2 plus 3. So what if we did 2 pi over 12 plus 3 pi over 12? And just to tell you what I'm aiming for is like I want to break this up so that the fractions simplify, so that I get some common factors in the numerator and denominator, so that I can reduce that 12 down. Because look what happens here. If I have 2 pi over 12, 2 and 12 have that common factor, so I could just write this as pi over 6. And 3 pi over 12, this simplifies to pi over 4. Now I'm looking at two radian values that I'm very comfortable working with. These both lie in the first quadrant of the unit circle, so I'm feeling good. The only issue is they're being added together inside of this cosine function. So how am I going to break this up and get this all in terms of, sine or cosine of pi over 6 or pi over 4? Well, I'm going to use this first formula right here. Okay, so in this, pi over 6 is basically my x1, pi over 4 is my x2. So let's break this up using that first formula right there. So I'm going to end up with cosine of x1, which is pi over 6, times cosine of x2, which is pi over 4, minus sine of x1, which is pi over 6, times sine of x2, which is pi over 4. Okay, and now I'm just evaluating each of these. So cosine of pi over 6, we have the unit circle up, so remember, we're just thinking about these terminal points. That terminal point on the unit circle at the angle pi over 6 is, the x-coordinate is root 3 over 2, the y-coordinate is 1 over 2. So cosine of pi over 6 is going to be the x-coordinate, root 3 over 2. And then, okay, cosine of pi over 4, that's that next angle there. I get root 2 over 2 for cosine of pi over 4. Okay, minus sine of pi over 6, that's 1/2, times sine of pi over 4, that is root 2 over 2. And now I'll just simplify. I can multiply these fractions together straight across. I get root 3 times root 2. I can do that just root 3 times 2, which is root 6, over 4, minus, and then in here I'll have root 2 over 4. And notice that I have common denominators here. Like I'm just simplifying at this point. I can take this difference and it's just root 6 minus root 2 over 4. I can put it over the common denominator. And is there any more simplification that I can do here? Root 6 doesn't simplify, root 2 doesn't simplify. There are no common factors in the numerator and denominator. All of my radicals are in the numerator, which is good, so I don't have to rationalize the denominator. I'm just going to put a box around this. Okay, I guess I could type this in my calculator if I wanted to, but it would be an approximate value that it would output, so I would just leave my answer like this. Okay, which isn't a super friendly looking value, but we were able to evaluate cosine of 5 pi over 12 despite us not knowing, or having pi over 12 in the unit circle. Like, we don't know that terminal point. So there it is. That's how we would apply that first formula to evaluate cosine at 5 pi over 12. What about sine of pi over 12? Let's try this one. So again, same dilemma, pi over 12. I don't have the terminal point memorized for this, nor do I have a pi over 12 triangle, like if I was doing the right triangle approach. Like, I don't have the sides memorized, right? For let's see, pi over 12, I guess that would be 15 degrees. Like, I can't do the opposite over hypotenuse for that. So I'm gonna have to try and break this up somehow so that I can apply one of those sum or difference formulas up there. Now, pi over 12, I'm not sure if I would want to break this up using a sum. I think a difference might be more helpful here. This is a pretty small value, so I could write this as a difference. Again, sort of thinking about like 2 pi over 12, 3 pi over 12. That was effective in that previous example. What if I did 3 pi over 12 minus 2 pi over 12? Again, aiming for that, getting fractions that will simplify. And that works, it simplifies down to pi over 12, and it allows me to apply, or first let's simplify. So this will be sine of 3 pi over 12 becomes pi over 4. 2 pi over 12 becomes pi over 6. All right, so now this is my x1 and x2, and I'm going to apply which formula? This is a difference, so it's actually going to be this last one. We're going to apply this last difference, sine difference formula. So I'll do that now, and I will get sine of pi over 4 times cosine pi over 6 minus cosine pi over 4 sine pi over 6. All right, so there it is, all expanded out. Now I just have to evaluate these. You can use the unit circle. You know what, I kind of feel like, just for fun, like drawing the right triangles. Remember, we can also use the right triangle approach here. So here's our like 45, 45, 90 triangle. Remember, the side lengths for this are 1, 1, root 2, and then the 30, let's see, so pi over 6, that's 30 degrees. So drawing a 30, 60, 90 triangle looks like this. The side lengths are 1, 2, root 3. Right, there's pi over 4. There's pi over 6. So sine of pi over 4 is opposite over hypotenuse. So that'll be 1 over root 2. Cosine of pi over 6. Cosine is adjacent over hypotenuse. So that'll be root 3 over 2. Minus cosine of pi over 4, which is 1 over root 2, times sine of pi over 6, which is 1 over 2. Okay, and I could rationalize these denominators. This becomes root 2 over 2. And then this is also root 2 over 2. So I'm getting root 6 over 4 minus root 2 over 4. So my answer is looking pretty similar to the previous one. This is root 6 minus root 2 over 4, and that's fully simplified. That can be my exact answer. Okay, so we actually got the same value. And one way to make sense of that we got the same value, is think about this triangle. You know, if this is like if that angle right there was pi over 12, this other angle right here would be 5 pi over 12. Right? Because remember, the angles in a triangle add up to 180, or pi radians. Right? And this right angle is pi over 2, and then these two should add up to pi over 2. So, you know, I don't know what these side lengths are. Like I keep saying, I don't have these values memorized, but like if this is A, B, and C, sine of this angle right here is going to be opposite over hypotenuse, so it'll be, you know, A over C. Right? And then cosine of this angle over here would be adjacent over hypotenuse. It would also be A over C. So it would be the same value. Sine of pi over 12 should be equal to cosine of 5 pi over 12. Okay, so this isn't really mandatory, you know, the stuff that I was just saying right here. But it is kind of interesting that we got the same value. I just wanted to show you why that is. But I don't want you to sweat that too much, because we've got 2 more formulas that require our attention. Here are 2 sum and difference formulas for the tangent function. So tangent of x1 plus x2 is tangent x1 plus tangent x2 over 1 minus tangent x1 times x2. And the difference formula, very similar. We're just switching this to subtraction and this to addition. Okay, so the signs in the numerator will match for each of these. Okay, that's the formula. You could derive this from the formulas on the previous page just by taking a quotient of sine over cosine. But we won't worry about that right now. Let's just try and apply this to evaluate tangent at yet another kind of strange, unfamiliar angle, 11 pi over 12. 11 pi over 12. So initially, to orient myself, like 11 pi over 12 in the unit circle, that is over here somewhere. Right, it's over there in the second quadrant. Right, and thinking all students take calculus A, S, T, C. Since this is in the second quadrant, sine is positive here, cosine is negative, tangent is negative. So I'm expecting a negative value here. All right, that should be less than 0. Okay, we'll deal with that at the end, but it's good practice to kind of size it up right as you're looking at it for the first time. All right, now how am I going to break this up? That's usually the first step, is like, can I break 11 pi over 12 up into a sum or difference so that the fractions simplify and I'm left with some radian values that are more familiar? Well, okay, 11, I think I'm going to do a sum, because 11 is a pretty large number. You know, I could probably break 11 up into, let's see, if I do 8 plus 3, 8 and 3 are values that simplify nicely with pi over 12. So let's try this, 8 pi over 12 plus 3 pi over 12. Okay, and you might try something else, you know, like if you tried 7 pi over 12 and 4 pi over 12, you might find that 4 pi over 12 simplifies nicely, but 7 pi over 12 wouldn't simplify nicely. Okay, so I'm choosing 8 and 3 because now I'm going to have tangent of, let's see, this will be 4, sorry, not 4. We have a common factor of 4, so we'll have 2 pi over 3, which is a good value, plus, and then 3 pi over 12, we saw this simplifies to pi over 4. All right, those are some friendly radian values. I know how to deal with each of those on their own. This is not the only way to do this. You could have done this, if there's another pair of angles that you think would have worked better, you can totally try that out. But I'm going to pursue this, and then, okay, we're going to apply the sum formula. So this first formula here, tangent of x1, so that'll be tangent of 2 pi over 3 plus tangent of pi over 4, that's tangent x2, divided by 1 minus the product of those two. Like that. All right, and now I just have to evaluate tangent of 2 pi over 3 and tangent of pi over 4. Once I have those, I can substitute in those values. So tangent requires a little more work. I might do a little scratch work over here. Just to evaluate tangent of pi over 4, tangent of 2 pi over 3. Let's start with tangent pi over 4. How do we want to evaluate this? We could do the right triangle thing, right? Maybe let's do that. So pi over 4, 1, root 2. You know, the angle here is pi over 4. That's a 45, 45, 90 triangle. This is the right angle. Tangent is opposite over adjacent, right? Opposite over adjacent, which is just 1 over 1, so that just equals 1. Okay, that's good. So we've got that one out of the way. How about tangent of 2 pi over 3? Okay, for this one, we could draw that angle real quick. 2 pi over 3 is right here. Okay. Now note that our reference angle is pi over 3 here, so t bar or t prime pi over 3. So what is tangent of pi over 3? We could draw a triangle, or you could do the, this is just sine of pi over 3 divided by cosine pi over 3. Sine of pi over 3, thinking about the terminal point on the unit circle, is root 3 over 2. Cosine pi over 3 is 1 over 2. This just simplifies to root 3. Okay, but all students take calculus, since this is in the second quadrant, really it's going to be the negative of this value. So really it's going to be tangent of 2 pi over 3 will be negative root 3. Okay. So now that we have those values, tangent of 2 pi over 3, tangent pi over 4, we can just plug, that's the hard part really. Now we just plug into the formula. So, okay, negative root 3 plus 1. Okay, doesn't look too bad. divided by 1 minus negative root 3 times 1, like that. Okay, and we'll just want to simplify that a bit. I might write this as 1 minus root 3 over 1 plus root 3. And let's rationalize that denominator. Remember, we don't like radicals in the denominator. I'll multiply top and bottom by the conjugate of the denominator. So take the sign or the sign of one of the terms in the denominator and switch it. So I'll do 1 minus root 3, multiply top and bottom by that conjugate. And when we FOIL that out, we'll get 1 minus root 3 squared in the numerator. Down here, if you FOIL it out, the middle term cancels out, and you're just left with, so 1 minus root 3 plus root 3 minus 3. The minus 3 came from root 3 times negative root 3. Okay, those middle terms there cancel out, negative and positive, and we're just left with negative 2 in the denominator. So I could write my answer as 1 minus root 3 quantity squared divided by negative 2. You could FOIL out the numerator if you felt like it, but this is how I'm going to leave my answer. All right, that was a pretty challenging one, right? We have to break up this angle, apply the formula, evaluate tangent at those angles, which is challenging, and then simplifying what we get when we substitute in those values. Example 4, we want to use sum and difference formulas to find cosine 2x. Cosine 2x, and this is actually foreshadowing some formulas that we are going to see in the next section. Double angle formulas is what they're called. But let's see how we would get this. Like, okay, cosine 2x. Well, the first step to sort of deriving a formula for that is we could break 2x into x plus x, right? Because once we write it this way, then we can apply a formula we already have. We can use the sum formula for cosine. So once we do this, I'll just keep working off of this right here. So cosine x plus x, we're going to get cosine x times cosine x minus sine x times sine x. All right, so going back to the list of formulas, we're just applying this first formula here. X1 and X2 are both x. So we get this. We can simplify this. What's cosine x times cosine x? That is just cosine squared x. Same over here, minus sine squared x. And that looks great. I'm going to put a box around that. And this is what we call the double angle formula. Okay, so we've derived our double angle formula. We'll see this again in the next section. I want to quickly show you that there are a few different forms for this, actually. We can rewrite this a couple different ways using the Pythagorean identity. This cosine squared x, remember we saw recently, I think in the previous section, cosine squared x is the same as 1 minus sine squared x. So if we make that substitution, 1 minus sine squared x, again that just comes from solving for cosine squared x in the Pythagorean identity. Okay, so just making that substitution right there. Another way that we could express this formula is 1 minus 2 sine squared x. Okay, so that's another version of this formula. And there's one more alternate version that we see sometimes, and it comes from replacing this, the sine squared x with 1 minus cosine squared x. The last form is 2 cosine squared x minus 1. So these are just 3 different ways of expressing the same formula for cosine 2x. Okay, but I'll save the rest for the next section, 9.3, where we talk about double angle formulas, half angle formulas, reduction formulas, and all that. So I'll see you in section 9.3.